Hello friends. So today we are going to solve the questions which are from the year 1990, 1991 and we have 1992. From the year 1990 we are having two questions. From the year 1991 also we have two questions, and from 1992 we are also having two questions. So in totality we are going to solve total 6 questions. So the first question, and it was asked in the year 1990, and it states that a thin prism P1 with the angle 4 degree made from glass of refractive index 1.54 is combined with another thin prism P2 made from glass of refractive index 1.72 to produce dispersion without deviation. The angle of the prism P2 is. In this case, there is a combination of two prisms P1 and P2 which only produces dispersion and there is no deviation. So under this condition, both the prism will be connected in such a way that their angles are in opposite. Angle of the prism are in you can say opposite side. That means if we have, this is suppose our first prism and this is our P1 having angle of prism as A1, and the second one will be connected in this way. So the angle is opposite. So this is our A2 and this is our prism P2. The only condition is that the deviation should be equal to 0. So it means if we have incoming on the prism number 1 and it is going to, you can say, let me draw. So this is our incoming ray and at 90 degree. So this will be, so this incoming ray should be such that it is able to mark in the extended version like this. So this is normal. So it is going to bend slightly towards the normal in this direction, and so this will be where we can say normal at this point, and it will be coming slightly in this format such that finally it is parallel to the our initial incoming ray. So from here we can clearly see that the deviation, that is our delta, is equal to 0. And we have to find out the angle of P2, that is our A2. Okay. And we know the relationship that for a thin prism, angle of minimum deviation that is our delta, it is given as mu minus 1 and angle, that is A. Mu is a refractive index and A is the angle of the prism. And it is given in the question that we are having dispersion but without deviation. So we can say for dispersion without deviation, the net deviation should be equal to 0, or we can say deviation produced by first prism, that is delta 1, should be equal to deviation produced by the second prism. Therefore, we can write it as our mu1 minus 1 a1 is equal to mu2 minus 1 times a2. So we can write that our a2 is equal to mu1 minus 1 divided by mu2 minus 1 times a1. So everything is given to us, we can just simply substitute it. We get 1.54 minus 1, and mu2 is given to us as 1.72 minus 1, and a1 is given to us as 4 degree. So we get that our a2 is approximately equal to 3 degree. So this was the angle of the prism for P2, that is 3 degree. Option C is correct. Option C is correct. Next question. And here it is asked that, it was asked in the year 1990, and it states that a narrow monochromatic beam of light of intensity I is incident on the glass plate as shown in figure. Another identical glass plate is kept close to the first one and parallel to it. Each glass plate reflects 25% of the light incident on it and transmits the remaining. Find the ratio of the minimum and the maximum intensities in the interference pattern found by the two beams obtained after one reflection at each plate. So here two important things are there. First is that it reflects 25% each plate, and secondly we have to find out the interference pattern or ratio minimum to maximum intensity after one reflection, and this one reflection should be from each plate. Okay, so these are the two important points in this entire question. Okay. And we need to find out you can say intensities, and for intensities we just need to find out the respective amplitudes, and from there we can easily find out what will be the ratio of the maximum and minimum intensities. So we keep in mind that one reflection should be taken from each place, and it reflects the 25%. So we can draw in a rougher approximate for that. So let us suppose this is our plate 1 and this is our plate 2. So this is our plate 1 and we are having plate 2, and incident light is given as I. So this is incident I, and in the first you can say reflection which is taking at plate 1, 25% will be reflected back, or we can say that I by 4 will be reflected back from plate number 1, and 3/4 will be passing through the plates. So this will be a 3/4 going forward, and it is going to strike somewhere here. So this will be our 3/4 times I, and here also the 25% is reflected back and only rest is forward. Okay, so it will be reflected back. So let us suppose it reflects somewhere here. So this is the point, and the reflection will be the 25% of 3/4 I, and that will be coming close to as 3I by 16. Okay. And from here rest will be passing through this plate, and that will be equal to our you can say 9/16. So this will be 9I by 16. And here at this point, once again, it is going to reflect 25%. So we are going to get 25% in this direction, and that will be close to 3I by 64, and rest will be passing back, and we are going to get this as 9I by 64. So this is the entire, you can see, reflection as well as passing through the respective plate. And we can just write this thing with the help of you can say some equations or formulas. So we are given that incident intensity is given as I, and let us find out first reflection that is taking place at plate 1. Okay. So you can say intensities after reflection and transmission. After reflection and transmission. So let us do it for first plate now. So the first plate, so the intensity reflected reflected let us call that as I2, and this I2 will be equal to 25%. So this is 0.25 of I, which giving us I by 4, and intensity transmitted and let us call that I3, and this will be 75%. So this is 0.75 times I, and this gives us 3 by 4th time I. Now we come to the second plate. Second plate, so intensity reflected let us call that as I4. This I4 will be 25% of I3, and this will be equal to our 25% of, that is our I3. I3 is our 3 by 4 times I. So this gives us that our I4 is equal to 3 by 16 times I. And similarly, we can find out the intensity transmitted. And intensity transmitted is suppose our I5. So this I5 will be equal to 0.75 times I3, and this will be giving us that our I5 is equal to 9 by 64 times I. Now we can calculate the amplitudes, because we are only interested, it is said that we have to find out after one reflection at each plate. Okay. So next we are going to calculate their amplitude. And we know that the intensity is directly proportional to square root of amplitude. Okay. So we know intensity is directly proportional to the square of the amplitude. Therefore, we can write that corresponding to I2, let us suppose the amplitude is A2. So we can say our A2 is equal to square root of I2, and this comes as square root of 1 by 4 times I, giving us 1 by 2 square root of I. Similarly, we can find out our A5, which will be equal to square root of I5, giving us 9 by 64 times I, and this will be equal to 3 by 8 and square root of I. Now we can find out their ratio. So we can say ratio R, which is equal to A2 by A5, and A2 was our 1 by 2 square root of I, and A5 was 3 by 8 square root of I. And here this I and I goes away, and this 2 goes with 4, so we are left with 4 by 3. Now we have to find out the maximum and minimum intensities. So we know the formula that max intensity, that is of I max, will be equal to R plus 1 whole square, and we substitute value of R, that was 4 by 3, so this comes as 4 by 3 plus 1 whole square, and this gives us 49 by 9. And we have minimum intensity, that is our I mean, which will be equal to R minus 1 whole square. So we get this as 4 by 3 minus 1 and whole square, and this gives us 1 by 9. And finally, we can find out the ratio. So we can say our I mean or max, ratio of minimum to maximum. So we can say this as I mean to I max is equal to minimum is our 1 by 9, maximum is 49 upon 9, this 9 goes with 9, and this gives us 1 upon 49. Okay, so the ratio is 1:49. Yeah. This completes this part of the question, and we come to the next question. It was asked in the year 1991, and it states that two parallel beams of light P and Q, separation D, containing radiations of wavelength 4000 angstrom and 5000 angstrom, which are mutually coherent in each wavelength separately, are incident normally on the prism as shown in the figure. The refractive index of the prism as a function of wavelength is given by the relation mu of lambda is equal to 1.20 plus 2b divided by lambda square, where lambda is in angstrom and b is a positive constant. The value of b is such that the condition for total reflection at the face AC is just satisfied for one wavelength and is not satisfied for the other. Based on this, we have two questions. First question, it says that we are having find the value of B. Part B, find the deviation in the beams transmitted through the face AC. And finally, a convergent lens is used to bring these transmitted beam focus if the intensity of the upper and the lower beam immediately after transmission from face AC are 4I respectively, find the resultant intensity at the focus. So we are given the figure, and this figure is a right angle prism A, B and C right angled at B. Two beams P and Q having a distance D are perpendicularly focused at the face AB. Okay. And the angle at A is given as theta. Okay. And we also mentioned sine of theta is point A. So first we have to find out the value of B, but the important point is here that the value of B is such that the condition for total internal reflection at face AC is just satisfied for one of the wavelength. It means one wavelength, either P or Q, will be totally internal reflected at the face AC, and we have to first of all find out which will be that particular wavelength, whether it will be Pu or whether it will be Q. So we can draw a figure for that, and this here angle theta, first wavelength, second wavelength. Let us suppose this is our P and this is Q. P wavelength is called lambda 1, Q wavelength is called as a lambda 2. Okay. So obviously, as they are perpendicular on the face AB, they will be traveling in a straight line and like this. And we have to find out which of the two will be internally reflected at this particular face, that is our AC. And so we are given that the lambda 1 is our 4000 angstrom and our lambda 2 is our 5000 angstrom. And the condition for total internal reflection, you can say for total internal reflection, light will be only total internal reflected only if the angle of incidence is greater than the critical angle. So we have to remember that for total internal reflection, the incident angle theta is greater than critical angle okay, and the critical angle depends upon the refractive index, that is our mu. Critical angle depends on the refractive index, that is our mu. So we can say that larger mu, larger is the refractive index, results in smaller critical angle. And this is also related with the wavelength, and we can say that smaller wavelength wavelength, this is giving us a larger mu, because the relationship is mentioned that our mu of lambda, it is given as 1.20 plus b upon lambda square, okay, resulting in larger mu. So therefore the smallest wavelength among lambda 1 and lambda 2 is lambda 1. So therefore we can say that the lambda 1, which is our 4000 angstrom, which is basically a shorter wavelength, will satisfy total internal reflection. And it is also given that our sine of theta is our 0.8, or we can also say that our sine of c is equal to 1 upon mu, and this gives us that the mu is equal to 1 upon sine of c. Okay. And one second, oh, my mistake. So we can say that mu is equal to 1 upon sine of theta. This gives us 1 upon theta is our sine of theta is given as 0.8. So we can directly write this value. This will equal to 1 upon 0.8, giving us mu will be equal to 1.25. Okay. So therefore the refractive index and we can also say from here that sine of theta is given as 0.8, giving us the theta is our 53.1 approximately. So we can say that for a refractive index, that is mu, which is our 1.25, is required to just achieve total internal reflection at 53.1. Now we can easily find out value of b, and we are going to use the relationship that mu of lambda is equal to 1.20 plus b by lambda square. We have this as 1.25, 1.20 plus b, and this is our 4000 and its whole square. So we can easily solve it, and this will be giving us b upon this will be 16 into 10 to the power 6 is equal to 1.25 minus 1.20 will be us 0.05, and this gives us that b will be equal to 8 into 10 to the power 5. 6, yeah. And if you convert into the, you can say the unit, I think, one second, yeah, so b is 8 into 10 to the minus 5, but wavelength is given in angstrom, So we can easily convert this into our and we get this as that the B will be equal to 0.8 into 10 to the power minus 14 meter square. Okay, both the answer is correct. Depends upon in which unit B is required. The second part of B is based on lambda, which is given in angstrom. Now we have to find out. Okay, so therefore we can draw, or rather we can say modify this figure, and here this will be acting, Q will be passing through, so we can just draw a normal here, and it will be going like this, and lambda 1 will be having a total internal reflection, so this will be in the downward direction. So this angle is theta, so we are going to have theta as well as our theta. Okay. And in this case this will be theta but is equal to I incident angle, and this will be our angle of refraction, and we can also find out here deviation, that this will be our angle of deviation, that is our delta, which we are going to just find out. Okay. The second part we have to do for part B, and part B find deviation. Deviation is for lambda is equal to 5000, that is our Q, that is our lambda 2, which is our 5000 angstrom. Okay. So we can just, we have our, this is our AC, and we have our Q, this is our lambda 2, and our normal, so it will be bending in this direction. So this is our angle of incident, this will be our angle of refraction, and the deviation will be, the deviation will be and the deviation will be, because it will be traveling somewhere straight in this direction, so this will be our deviation, incident ray as well as refracted ray. And we can use the formula, or the, you can say the equation that is given to us. We are given as mu is equal to 1.20 plus B, and this is our now 5000 whole square, and B we already know, so we can just substitute it here, and B is our 0.08 into 10 to the power minus 14, so this gives us that mu will be equal to 1.232, and we can use Snell's law. So we can say, using Snell's law, we have that refractive index mu will be equal to sine of R divided by sine of I, and sine of I, that is of sine of theta, is given to us, that is our 0.8. So we can write that our sine of R is equal to mu times sine of I, not theta. I and theta are same in this case, so we get this as mu we just found out is 1.232 multiplied by 0.8, and this gives us 0.9856. Therefore, our R is equal to our sine inverse of 0.9856, and that will be approximately equal to 80.3. So the refracted angle is our R, that is equal to 80.3 degree, and we need to find out the deviation. So from the figure itself we can see that this angle will be just opposite to I, so this will be over I, and this whole angle is our R, so deviation will be equal to our R minus I. So deviation, that is of delta, is equal to R minus I, and this gives us that 80.3 minus 53.1 is equal to 27.2 degree. And we come to the last part, that is part C. And in part C, it is said that the converging lens is used to bring these transmitted beams into focus. If the intensities of the upper and the lower beams immediately after transmission are from AC are 4I and I, find the resultant intensity at the focus. So we have to find out what will be the resultant intensity at the focus. So in this case, it is saying that both beams are getting transmitted from the face AC. And because we can say that we have, one second, let me check again what is given. Transmitted if intensities of upper and the lower beams immediately after transmission from the face AC. Okay, so their transmission immediately after the face AC is given as 4I and I. Okay. So therefore, we can say or draw in a rough approximate figure. So this is our A, B and C, and we are having two beams, both are parallel to each other, and suppose this is point P, this is our Q, and we have a normal that will be like this, and this will be moving something like this. Let us suppose this is our S, and if we draw a perpendicular here, this will be our R. And we have our angle of incident, and this will be our angle of refraction, and this will be also our angle of refraction. Okay. And we have to remember that only 5000, that is lambda 2, is coming out. Okay. So we have to keep in mind that only lambda 2, which was our 5000 angstrom, is coming out. So let us call this as ray 1, and let us call this as ray 2. And we have to find out, first of all, the path difference between ray 1 and ray 2. path difference between ray 1 and ray 2, and that is a delta x, which will be equal to mu and multiply by qs minus, and that will be a PR. And we can use some triangular property, and we have our, we can say that our sine of I will be equal to qs upon ps, and here this will be also our I. Okay, so sine I is equal to qs upon ps, and we can find out our sine of r. Sine of r is equal to PR upon PS. So if they find out their ratio, that is sine r upon sine I, you can write that sine r upon sine I, this gives us PR upon PS, QS upon PS, and this comes as PR upon QS, and that will be equal to, because sine I of sine r is nothing but our mu. Therefore, we can write that mu times QS is equal to PR. So it means if we substitute this into the path difference equation, we can say that now our delta x will be equal to delta x will be equal to PR minus PR giving us equal to 0. Therefore, there will be no path difference, and thus we can also say that from here we can say that phase difference between ray 1 and ray 2 will be equal to 0. Phase difference between ray 1 and ray 2 will be 0, or we can say they are going to interfere constructively. Okay, so it means constructive interference. Constructive interference. Therefore, we can say that maximum intensity, that is our I max, will be equal to square root of I1 plus square root of I2 whole square, and they are given as 4I plus I and whole square, and this gives us that our I max will be equal to, this will be 9I. So we come to the next question. It was asked in the year 1991, and it states that a slab of material refractive index 2, as shown in the figure, has a curved surface APB of radius of curvature 10 cm and a plane surface CD. On the left of APB is air, and on the right of CD is a water with refractive index as given in the figure. An object O is placed at a distance 15 cm from the pole P as shown. The distance of the final image of O from P as viewed from the left is. So we are given this figure and it says that, so this refractive index is 4/3 actually, and an object is placed at this point O. See the center of curvature of this object, you can say slab, and on the right side of CD, which is a, you can say, plane surface, we have a water. So here water is there. On the left side we have air. So here we are having air and here we have a water. And the respective distances are given. Pole and this plane surface is given as 20. Pole and image distance is given as, object distance is given as 15 centimeter. So we can draw an approximated ray diagram for it. And we know for the curved surface, the normal should be going through the center of curvature, and we are going to have a ray which will be coming from the object in this direction, and it will try to bend something like this. And if we extend in the backward direction, it will be going like this and somewhere here. So this will be a virtual image. Let us suppose that is called as I. Okay. And we can use the basic formula, that is our, you can say, mu2 upon V minus mu1 upon U is equal to mu2 minus mu1 divided by R, where mu1 is the refractive index where object is located, mu2 where image is formed, and U and V are the, you can say, distance of image as well as object, and R is the radius of curvature. And for this particular question, mu1 is given as 2 and our mu2 is our 1, and radius of curvature will be equal to minus of 10 because it is towards the object, or you can say towards the left of the object, and our U is equal to minus of 15. Okay, because once again the rays are traveling towards left and object is toward the right. Therefore we can just substitute the values. We get this as 1 upon V minus 2 upon minus of 15 is equal to 1 minus 2 divided by minus of 10, and this gives us that the V is equal to minus of 30 centimeters. So it means the distance of the image from the pole will be 30 centimeters. So this will be 30. Centimeters. And CD is a plane, you can say, surface, and because the image is virtual, so this plane surface is not going to have any effect on this image formation. So it will be straightforward traveling across surface CD and focusing at I. So we can say that the image is virtual, so therefore the rays never actually pass through surface CD, plane surface CD, plane surface CD. Thus, we can say that no refraction occurs at CD. No refraction occurs at CD. Therefore, the final image remains at 30 centimeter from P. So it means this CD has no effect on this. So the distance of final image from the point P is equal to 30 centimeters. So we come to the next question. And it was asked in the year 1982, and it states that a planet is observed by astronomical refracting telescope having an objective of focal length 16 meter and eyepiece of focal length 2 centimeters. So based on this, we are having 4 questions. And in the first question, it is said that the distance between the objective and eyepiece is 16.08 meter. The angular magnification of the planet is -800. C, the image of the planet is inverted and the objective is larger than the eyepiece. So we are given that the focal length is 16 meter and the of objective and eyepiece is 2 centimeters. So we have to make sure that these two units should be same. So we are given objective focal length that is of FO is given as 16 meters. So this will give us 1600 centimeters, and we have eyepiece focal length that is our FE, and which is given as 2 centimeters. And it is said that and the separation between we can say that the astronomical, because it is said planet is being viewed, so planet is, we can say, is very far, therefore we can presume that the telescope is adjusted for normal viewing. We can say that astronomical telescope is adjusted for normal viewing. So which means that final image is at infinity. Final image is at infinity. So now we can use the standard formula that the distance between the objective and eyepiece will be d, and that is a summation of their respective focal length. So we can say separation between separation between the objective and eyepiece, that is our D, will be equal to focal length of objective and focal length for eyepiece. And also we can write that the angular magnification, that is M, will be equal to minus of FV upon FE. So it means image will be inverted. From here we can just negative sign. So we can say image is inverted. So let's use the formulas. So we get D is equal to FO plus FE, which is our 16 plus 2, giving us 1602 centimeters, and that is our 16.02 meters. And we have to find out the angular magnification, that is equal to minus FO upon FE. This is minus 1600 by 2, giving us minus of 800. And like I said, the image is inverted already, and the final one is the size of object. And in telescope, the objective size is always larger as compared to eyepiece, so as to be able to gather the more light. So you can say in telescope, objective lens is always much larger than eyepiece to gather more light. Gather more light. Therefore, all these options are the correct options. So we can say option A, B, C and D are correct. Okay, so we come to the next question, and here it was asked in the year 1992, and it says that light is incident at an angle alpha on one planar end of a transparent cylindrical rod of refractive index n. Determine the least value of n so that the light entering the rod does not emerge from the curved surface of the rod irrespective of the value of alpha. So basically means we have to find out that the ray should be suffering total internal reflection. So it means it will be bending something like this, and this will be normal here, and it will be going like this. Okay. So total internal reflection. So this angle is alpha, and this angle is our R, and let us call this angle is our R prime. So we can say that light never emerge from curved surface so it means total internal reflection, and it means that every point on this curved surface the angle of incident must be greater than or equal to the critical angle for total internal reflection. So you can say that at every point on the curved surface, the angle of incident inside the rod, inside the what is this rod? Yeah, inside the rod must be you can say greater than or equal to critical angle. For total internal reflection. So therefore we can say that the critical angle, if that is written as theta c, is the minimum angle inside the denser medium or inside the total rod for which the total internal reflection occurs. We can see that our critical angle, and if we represent it as a theta c, is minimum angle inside the rod, and that is basically our denser medium for which total internal reflection occurs at the boundary with the rarer medium. At the boundary with rarer medium, and this rarer medium is our air. So we have to find out the minimum refractive index, that even the smallest angle causes the total internal reflection. So that's our final target. And we know that our sine of theta c, that is critical angle, is equal to n1 upon n2. Okay. So here theta c is our critical angle. And for the curved surface, at curved surface, this you can draw a right angle triangle. Let us call this as point as P, this as Q, and this is R. Okay. So we can draw a right angle triangle. This is our P, this is Q and R. So this is our R and this is our R prime. And this is our 90 degree. So we can say that our R plus R prime is 90 degree, and from here we can say that our R prime is equal to 90 minus R. And if you want that our R prime is to be minimum, R should be maximum. So you can say our R prime, if you want to be minimum, then 90 minus R, this should be our maximum. And we can use the Snell's law at the plane surface. Snell's law at planar surface, and the refractive index, that is our n, is equal to, we have this is sine of r, which should be maximum, and accordingly we are going to have sine of I, that should be also our maximum. But the maximum value of I here, which is our alpha, you can say, but maximum value of I is our 90 degree. Okay. Thus we can say that sine of 90 is equal to 1. Therefore we get that our n is equal to sine of r, and this is our maximum. And we can also write that our critical angle will be equal to 1 upon n, and thus we can say that our R max is equal to our critical angle, and we already know that our R prime minimum, and we can say this gives us that R prime minimum will be equal to now theta minus critical angle. And from this equation we can write that for total internal reflection at curved surface for all rays, the condition is to satisfied is that our R prime minimum should be greater than equal to our theta c. Okay. So we simply substitute the value, we get this as our 90 minus theta c is greater than equal to theta c. This gives us that sine of 90 minus theta c is greater than equal to sine of theta c, which we can write that cos of theta c is greater than equal to sine of theta c. Okay. And from here we can write that cot of theta c is greater than equal to 1. Okay. And we already know that the sine of theta c is equal to 1 upon n. Sine of theta c is equal to 1 upon n, and we are going to use the identity that a sine square theta c plus cos square theta c is equal to 1. So this gives us that cos of theta c will be equal to 1 minus sine square theta c and its square root. This giving us 1 minus 1 upon n square and its square root. So we get that cot of theta c is equal to, we have cos of theta c divided by sine of theta c. We substitute the respective, and theta c is our sine of theta c 1 upon n, and this is 1 minus 1 upon n square and its square root. So this gives us square root of n square minus 1. So therefore the cot of theta c should be greater than 1, and from then we can write, we know that cot of theta c should be greater than equal to 1. So this gives us the square root of n square minus 1 should be greater than equal to 1. And now it is simple calculation. We can write this as that n should be greater than equal to square root of 2. Okay. So this is our value of the refractive index which we are supposed to find out. Okay. So we have to find the least value of n. So least value of n will be equal to n is equal to square root of 2. So least value of n, that is a refractive index, should be equal to 2. For this value, all the rays will be having total internal reflection irrespective of the angle, that is our alpha. So I think this completes. Yeah. So these were the questions which was asked in the year 1990, 1991 and 1992, total of 6 questions. So this completes all the 6 questions. Thank you.